So hello, everybody. Good afternoon. We're ready to start. Thank you for joining once more. Hope you are all safe. And what I'm going to do now is to share my screen. Just 1 second. Okay. Ready to go? Okay, so this is then our 4th live lecture. Today, it may take a bit longer than usual because I'm going to do at the very end some kind of Blackboard style derivations. The topics we are going to we are going to cover are related to the asynchronous lectures. So in lecture 4, part 1, we discussed density matrix of compound systems. In part 2, we applied these to spontaneous emission. And then in part 3, we started to talk about WKB approximation, which is a very powerful method for dealing with tunneling and transmission through azimuth potential. And here we had some derivations related to that, and we talked about connection formula. The asynchronous lectures are here. I will apologize to the intercollegiate people. I tried to upload some files on Friday and at the weekend, and there were always blue screen crashes in my computer, which was really annoying. But as you know, I'm still trying to sort out the problem. I mean, I'm not quite happy about corporate firewalls, to be honest. Fingers crossed. If you have any trouble afterwards with understanding, I mean, I'm doing my best to upload them, but I know the situation is not ideal, so I apologize for that. But I will do anything I can to mitigate the situation, and I'm trying. So what we have covered in the synchronous lectures are the following topics. We discussed density operator formalism, and especially putting emphasis on subsystems of entangled states or entangled systems. Then it was all about advanced wave mechanics, WKB approximation, what ansatz you have to make, derivation of the formula, the failure of these wave functions at classical turning points, connection formula, and applications. I'm going to cover today one to give you an example of how this works, and there's going to be another one next week. So also problem sheet 1 is online. If you go to week 4, you'll be able to download it. The topics go from the beginning up to entanglement and applications and reduced density matrix. Don't take this time too seriously. Obviously, if you are in a different time zone and you cannot make it, I'm not going to make a fuss, but please do upload on the 10th of November. I'm going to make an entry on Moodle so that everybody can upload their sheets. The total number of marks is 30. Also, please scan your work, save it as a single PDF, and submit your sheet to me. Try to make a PDF not too large, and this is a please, 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 because you are seeing what happens to the videos. I don't have the best bandwidth, and these files need to to be downloaded, corrected, and then uploaded again by the markers. I don't know what the situation is. So if your file is too large, please compress it. You'll find plenty of online tools. I mean, at least from my side, I can handle up to 10 mega, but more than that, things are going to go crashing and burning, and we want to make them as small as possible, but still good quality. So there are plenty of online tools which can be used to compress PDFs, and also make sure that your completed work is clearly labeled with your name and college. And please note that UCL places penalties, which are quite tough on late submitted work. So this is quite a nice sheet, because you are going to see information about many topics that we have covered here. And this is going to be some question. Let me see. I think according to the regulation, student numbers. But if you have to upload, I'm going to see it anyway. So, you know, there are all these privacies, but you have to upload it to Moodle. So, I mean, you just have to ensure that you are identifiable. If you upload, we know who you are anyway. But I know that there are some privacy concerns and some privacy laws. Just make clear this is identifiable, because it is going to be much more work to find the person, give the mark sheet back, the markers will have to upload it, etc., etc. So if you want to put your name, put your name, but we're going to know who you are anyway, because you are going to submit it via Moodle. So I think this, with this crazy pandemic, is like we're living all a bit in Black Mirror, right? That the usual roles are not applying, which is it's weird for everybody, but we're all trying to cope. So why is it not moving? I hate this. We had a few things for you to try. I know this, like, hope you tried this at home sounds a bit passive aggressive, but it's just to make the point. We had a few things for you to have a look at and get used to the formalism and the situation. And one thing that we wanted is if you would use disclosure relation for the momentum representation, show that these holds. And what you have to do is you pretty much have to start from normalization condition that you know psi is normalized, include here the closure relation on P, which you know D3P, PP is equal to the identity operator. Then when you do that, you obtain this expression. And if you compare with what you know from P representation, we know that D3P psi star P psi P is equal to 1 for normalization. So if you compare here, there should be an arrow related to the vector. You find that this holds. How you compute. We're getting to spontaneous emission. My suggestion is to write whole specifically in terms of the compound system, and then you sandwich. Remember what operator and what cat works in what subspace. This is something that is really important. This is related to the asynchronous lecture, right? So there was another thing which was also straightforward but instructive, is when you deal with operators of continuous basis, and you had the operator px, and you needed to show that px in the momentum representation is given by that. So what you do is you insert closure relation on one side, closure relation on the other side. Then you are going to end up with these expressions. Here there is a hat, sorry, I forgot. And you have then this expression, but you can apply using the eigenvalue equation that you know that if you apply px, the operator to the right, and looking from what we know from compound systems, we know that this is an eigenvector of px. If you want to do it slowly, write this p dash as the tensor product of p dash x, p dash y, p dash z, and then you will see that this guy is going to operate only on px, but it's pretty much how you would proceed. And here you have to consider orthogonality, that once you have moved from being an operator to being a quantity, like a variable, then you have this orthogonality relation, and you find then that because you have delta p minus p dash, that you Q1 integral using properties of delta functions, and you end up with this. Then we also said, have a look at expectation values of operators. So there were a few properties. So first we had this thing related to expectation value of an operator being the trace of the operator applied to ρ, which is the density operator. Then we had ρ, and we had some interesting properties. And I said, okay, you don't need to prove linearity, but let's prove hermiticity. Let's prove that the trace is unitary, and let's prove that you have non-negativity. And hermiticity is easy, because what you do is when you go from ρ to ρ dagger, you pretty much just have to swap this bra and this cat, so it's going to give you the same result. And here, Pj is going to go to the complex conjugate, but we know that probabilities are real. So Pj star is going to be Pj, and you're going to get pretty much the same result. Now, to have a look at unit traces, remember what a trace is. So you're going to have sum over k of ρ kk. If you compute ρ kk, you're going to get that this is the probability pk. And the sum over k of all probabilities has to be 1, right? And one way to prove, to show that the density operator is positive semi-definite is you consider a state psi, and you apply it here, and you see that you're going to get something that is bigger than 0. And you know that inequality is going to follow because you know that these probabilities are going to be bigger than 0. This modulus square here also. So it has to be this way. So we're going to start reviewing this lecture. Any questions so far? I wanted to do this, stop video, and I'll share again. So we're going to start reviewing these lectures, and what we're going to talk about is density matrix of compound systems, which is a topic that is quite useful, especially if you're dealing with entanglement. And you construct this density matrix in pretty much the same way that you would construct for a system that is not compound, but you have to bear in mind that here you're going to have compound states. So the states, they are formed by the tensor product of AJ cat, BK cat, and Al bra B, and bra. And you're going to have then this kind of density matrix. And reduced states are very useful if you are dealing with a compound system, because if you have also an entangled system, you cannot separate the state vectors of individual subsystems. So imagine you have a compound system which is entangled. How do you operate with that? How do you go with that? Well, that's why we need reduced states. This is in fact very powerful, because if you're dealing with a product state, it's easy because you can factorize the state of your compound system into a tensor product, and you can say, okay, this belongs to subsystem A, this belongs to subsystem B. So the reduced state is the state that allows you to calculate the value of any observable which acts solely on a system A, for instance. In other words, for any measurement of the properties of system A which ignores system B. So this is a way of erasing the contributions associated with system B from an entangled state of a compound system. And to do this, we need partial trace. So how do you compute? Well, just remember, we just saw the trace is given by this expression. So you sum over J and K in a compound system when you have whole JK, which is given by this. So what we would like to do is we have a density matrix, and we would like to erase the contribution of a subsystem. So for instance, system A is traced out. What do? You sum over the degrees of freedom or over the indices that are associated with system A. And you end up with a density matrix, which is only going to depend on indices associated with B, whole B. So this is pretty much what we're trying to achieve. And is a way.
Sorry.
Yes, hang
on. Because the rho JLJM,
yeah,
they still have something to do with system A. So when you wrote down like 2 slides before, the way that rho
let me go here. Let's go back.
Yeah, exactly.
JKLM.
Yes.
So we have this, and then we have that as well.
Exactly.
Right.
And when you, and there it actually depends on A and B. So
yeah,
the coefficients still depend on the basis of the other system. So even if we do the partial trace, doesn't that still mean that it at least have some dependence on what A and B are?
I mean, that's the tricky thing. You're trying to disentangle this, and you're going to carry something along, correct? But you want to erase the influence of one of the subsystems as much as possible. So it is quite difficult to do that, because the system is entangled for in the first place. But if you cannot resolve certain variables, typically what you do is you integrate or you sum over those variables, and this is a bit of the spirit.
Okay, but because for me it makes at least a little bit sense that it is not completely not affiliated with system A. So these components kind of take into account that we actually have an entangled state. Could I say this? So
yeah, but it also takes into account that you don't know what it is.
Yes, exactly. But it's not like we completely separate it, because in these coefficients we still have the compound state of A and B, and they kind of depend on this.
The coefficients will depend on this, yeah. I agree.
Okay.
But you are trying to erase the influence of one of the systems as much as possible.
And for that we just fix the index and then sum over it.
Yeah, you sum over it.
Okay.
Is, for instance, if you're trying to make a measurement and there are coordinates you don't know and you cannot resolve, a way to express your ignorance, if you wish, is to integrate over these coordinates, which would be what I wrote down, but for a continuous basis.
Okay, great.
See?
And I don't know if you come to this, but if you could maybe explain again how will we solve this EPR paradoxon? If you
we can come to it.
Okay.
I'll give you an example. The key issue is you have an entangled state.
Yes.
And this entangled state is, I was saying, okay, try to compute this as an example. Okay, so I'm going to come to something similar.
Yeah, no worries.
We have the partial trace, right? And if you want to calculate the expectation value for observables that act on B alone, you have then to apply this operator that you want to compute on whole B, not whole, because then you kind of traced out A and you're looking then at B. And if you want to trace out B instead of tracing out A, then you have to sum over indices associated with B. Chat. Cannot, I'm trying to get chat. Okay. Yeah, I just not seeing it. Anyway, I'll go back there, but let me continue. Because one important point here is that the reduced state of the system is a pure state only if the system exhibits no entanglement. And reduced states of entangled systems are always mixed states. So do try this at home. This is a bit what you asked me. Someone asked me about the paradox, EPR paradox, is you consider the entangled state of two spin-half particles, and you can see they are in a compound state, right? Both have either spin up, it's a coherent superposition, or both have the spin down. You cannot disentangle them. And what we would like to show is that the reduced state of the system B is given by this expression. So we're going to trace out everything that is associated with system A. Now, a very important issue here is, and this comes back to the paradox, is that if you are naively speaking and you would look at this wave function, you would say, okay, if I measure one spin, I will know immediately what the other spin is, because let's say I apply an operator that gives me for system A psi A, because I don't know what, because they are entangled like this. So I know immediately, and the information is being transferred. And that is the difficulty people were getting at, faster than the speed of light, which would then contradict general relativity. But you have one issue here. First issue is that this entangled state, you are not really separating electron 1 from electron 2. This is an entangled state for both particles, which means that you cannot really say electron 1 is sitting here, electron 2 is sitting there. This is may even be the case, but the quantum state is describing everything, and you cannot factorize it. So if you were a physicist performing an experiment and you didn't know what system B or A was doing, what you would have, you wouldn't have just one state, you would have a mix. Can you see this whole B? This is what you would have. You would have something like a density matrix of a mixed system, a mixed state. And this is because it's entangled. So here we traced out everything which is associated with A. You don't have any information. So is the question, a physicist that doesn't know anything about A, would they have any information about B just being one thing? And you find that you still have here up and you have down. So this is a bit of the difficulty. You have to see how your state is constructed and that they are entangled. So you don't have like this local thing going on, that information, something happens here and is transmitted immediately. It's a bit tricky, but that is a bit the idea behind it. So another issue that we discussed, and there were some questions, that this is related to the heuristic model of spontaneous emission. To do a proper model, we need to quantize the field. But if you want to do something heuristic, and this is in some example, which is in part 2 of lecture 4. Now it's coming. Okay. So I think partial trace is like calculating a marginal probability distribution if you compute, which depends on what the full is. Yeah, exactly. But in effect, you only care about probabilities of one variable. That is more or less what you do. You cannot resolve the other probability. So it's, I mean, I don't know if you have ever modeled experiments. Sometimes you are given the moment of 2 electrons and you say, okay, I don't know what certain components are, and then you integrate over. So you don't have the full probability density, but you are just analyzing the probabilities of one variable. And then Alberto, if you have an open system that you want to reduce, how do you define the base for all the other external systems? You may not know it. Yeah, this is a very good point. We're going to see this at the end of the course. And it can be pretty tough. Sometimes you have to guess and you have to make assumptions about your bath, but what you would have is you would have a system and a bath, and you consider these external systems which you don't know as some kind of bath, and you focus on how your subsystem interacts with it. You know, is a very good question, because this has plagued many people's lives when they're trying to model open quantum systems. This is a very good point. Hi, in spontaneous emission, why do you consider? Well, we're considering 2 things here, because you say in spontaneous emission, why do you consider psi-t as a pure state? Isn't it a linear combination of excited and ground state, each associated by the associated, which multiplied by the associated probability? No, because you have to consider the light, you see? So what you're talking about is this guy and this guy, which is the atom. But what you have is you have this, and this is the 0 photon state, and this is the 1 photon state. So in fact, you are defining a compound state for not only atom, but you're considering light as well. So in your mind, when you asked me this question, you are already automatically tracing out the states that are associated with light. Can you pay attention? Can you see when you say, okay, you're only talking about the atom? Yeah, if you only talk about the atom, yes, I agree with you. But you are considering also light. So your system is not only the atom, your system is light. So you are going to have a coherent superposition. Your state psi-t, which you let evolve, is going to be a coherent superposition of an excited state, which is the atomic state, tensor product with a 0 photon state. And you put this here. and plus, and this is square root of 1 minus this probability, the probability associated with this amplitude of it being the ground state and one photon when one photon has been emitted. Can you see the difference? It's not only the atom, you're considering atom plus light. I warn you, this is heuristic. If you really want to describe spontaneous emission, you have to quantize the field and you have to look at how you deal with vacuum modes. It's pretty cool, but I'm not going to do this here. So now we write the density matrix. You see, so you have psi t, so psi t get psi t bra. For the compound system, emphasis on compound, this is going to be pure. You just have this guy. But here you see that you have a lot of things which are given by the sum of all these coefficients here associated with these tensor products. So if you want to get rid of the photon modes and you trace out, you see that you have whole atom is going to be, you trace out the components of light. So to trace out, you use those expressions has been done a bit more in detail in the asynchronous lecture. But now you see that your reduced state, and we come back to Honey's point, is mixed. Not your full state, but your reduced state is definitely mixed. And you're tracing out over your photon modes. So you end up with something which is what you described when you asked your question. You have something that incorporates the excited state, something that incorporates the ground state, and they have some kind of probabilities or in front of them. Okay? So we have also discussed time evolution. So if at a time t, the system is in a state described by this density matrix and you let it evolve, so you apply u, and you also write this as, for the bra, as the u dagger, then you can see you have a transformation. So you just have, you don't have any change apart from this change of basis that is going on here. So a system that is initially pure will stay pure under unitary evolution. There may be other things that are going to mix it. For instance, you can have classical uncertainty. You can have the situation that the system can be entangled with other systems. And this is something, for instance, that is very important, once more, when you are dealing with open quantum systems. Is that clear? And this is something new. This is a new topic, which is related to Wenzel-Kramers Brillouin approximation, so WKB approximation as it's known. And the motivation is to look at tunneling and transmission for potential of arbitrary shapes. I mean, we all have considered the time-independent Schrödinger equation for square wells or things that we can solve analytically, but nature is messier. Many things that you do, you're not going to be able to solve analytically. So we consider particle of energy E, and it's described by the time-independent Schrödinger equation. And this guy now, instead of being, so he has this energy, and this, instead of being a fixed square well potential like Vx equal V naught for some kind of interval in X, is something that varies smoothly. And WKB approximation is going to allow us to solve the time-independent Schrödinger equation for potentials Vx that are varying sufficiently slowly. And they're readily applicable to 1D problems or problems reduced to 1D. For constant potentials, normally what we have is we can define a momentum. We have a de Broglie wavelength, and we are going to have something similar. We're going to generalize this for slowly vary potentials, but we need to be careful and we need really to make sure that this picture still holds. If this potential varies in some kind of crazy way, you're not going to be able to do that. So the WKB wave function, this is also what you do is, if you have the idealized case, Vx equal constant, you write the wave function as a E I H bar, and then you have some kind of P, right, X, or you have then minus Px depending on the direction. But so you're going to make a similar ansatz, but you're going to generalize this. So you are assuming it looks like that. And what you get, if you insert into the time independent Schrödinger equation, the tail derivation is given in the asynchronous lectures. So if you are a bit hesitant on how it goes, do have a look. And if you have any questions, do let me know. So you have an equation that is nonlinear, looks a bit more complicated. So far, this is exact. You see, this is given, this is the second derivative of x, of Sx, and this is the first derivative of Sx. So I'm using here dashes as derivatives. And this is exact. Looks more complicated, but it has some advantage because we can expand this as a power series in h bar. So we're going to assume that Sx is S0 plus h bar x1, blah, 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 up to infinity. And at some point, you're going to truncate. If you do that, and you plug in this time-independent Schrödinger equation, you get this type of expression, this series, and you're going to need to look at what happens term by term. For instance, I'm going to go, WKB, in fact, you can do it for more terms if you need to, but in WKB, what we do is we consider zeroth order and first order. So you have this expression here, and if you solve for zeroth order, you get S0x plus minus integral of x gx dash px dash plus a constant. Note that if this guy were constant, p were constant, which is what we have when v is constant, you would get back to that expression that we know, which is plus minus px plus the constant. And to first order, if you look at the first order term, you get something like this, which you can rearrange, integrate, and you get a logarithmic function of S0 dash x. And this is equal to something depending on x1. So for WKB wave functions, meaning if you can show, in fact, that if the potential is smooth, you can neglect the other orders, meaning if it doesn't vary that much with regard to the system's de Broglie wavelength that you generalize for this case. So you make this approximation, and if you plug in and you look at the expressions that you had in the previous page, you find psi x a square root of px e I x px dash gx dash over h bar plus b square root of px e minus x e integral over x. So you have plus here and minus here to counter or to express the fact that they may be propagating in two directions. And px is given by this expression, which is again similar to what we have when we consider quantum a fixed potential, with the difference that here your v is variable. Now pay attention, because so far we haven't made any assumption. Is this classically allowed? Is this classically forbidden? If we are in a region that is classically allowed, we know that this px here is going to be real, and that these wave functions are going to propagate. They're not going to grow exponentially or decrease exponentially. So we haven't made any assumption, but in how it's written, it's actually more convenient for classically allowed regions. Now, if we consider a classically forbidden region, meaning if you say that the energy is smaller than Vx, it's more convenient that we don't have anything, because in this case, we would have something complex here, and it's not that convenient for us. So it's much better to rewrite it in this way, and then have our psi x defined as a function of qx. Here we have square root of qx, and here we have, because qx is like px is going to be I qx, if you would substitute it here, you would get like a plus and a minus sign. So one is exponentially decaying, the other is exponentially increasing. So this looks all nice, but it breaks down when you are close to a classical turning point. Classical turning point is when this term here is 0. So when E is equal to Vx, why does it break down? You can see immediately that these expressions here, and also here, they're gonna diverge. So it's not going to quite work out as expected. And when you're dealing with barriers, when you're dealing with transmission, when you're dealing with reflection, you are going to always find some kind of classical turning points. But our WKB approximations, they are asymptotically valid, meaning that they can only be used if you are far enough. So you need to find something that you can use in the intermediate region. And we know that if we have an exact wave function, this would be smooth and continuous everywhere it has to be, because you associate a wave function with a probability amplitude. And if you compute probabilities later on, it doesn't make a lot of sense, physically speaking, that you're going to have singularities or crazy stuff, right? So the question is, what can we do with that? How can we join the two types of WKB solutions across the turning point? And that's why the task that you have when you look at connection formulas, you have to find an addition of wave functions, which are valid in the region for which the WKB is not valid, namely in the vicinity and at the turning point. And asymptotically, they have to converge to the WKB solution. So near the turning point, Vx is approximately linear. So what you can do is you can expand the potential around A. What is, I don't know, this A, I wanted to make small a and I put capital A, sorry. But it's pretty much A is a turning point, small a, and A capital is this expression which you get for your Taylor expansion. So you expand this in series, and you have a time-dependent equation which is time-independent, sorry, which has a linear potential. And if A, which is this coefficient here, is bigger than 0, you have what we call a right barrier. I mean, why we can assume that you can take H bar going to 0, why you can consider the system to be in, this was before, I'm seeing only now, I'm not getting the notification somehow. But why can you consider that a system is in a pure state when you had this density matrix? On the left-hand side, you had a single projector. On the right-hand side, you had a sum of multiple projectors. It depends on what you're looking at, because On the left-hand side, you were considering atom plus light. So this is what we call change of basis. Atom plus light is your compound basis. So that psi t is actually a tensor product of things related to the subspaces, but the whole wave function is just psi. So it depends on the basis you are working, but the physics shouldn't depend on the basis. So that expression that you had on the right-hand side is something that you were using to construct your compound state, but your compound state was only one, was psi. And someone asking about the limit of h bar going to 0 when it's just a constant. A way of looking at this is what we call semi-classical limit. So h bar is very, very small. And if you are in some kind of classical regime, you say it's just a constant, but it's a trick for us to see, okay, how classical is our system, because it means that everything else would be much bigger. And a question is, why can we assume Vx is approximately linear? Remember Taylor expansion, right? If you have any function, you can expand it in series. So you're going to have, if you do it rigorously, around the turning point, you would have dvx, gx, x minus a plus 1/2 d2vx, gx square, x minus a square, plus blah, 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 up to infinity, right? If you're close enough, then this means that x minus a square is going to be much smaller than x minus a, unless the second derivative of v at that specific point is huge, which would mean your potential is not going to be that smooth anymore if you have a huge second derivative. Then it is something totally crazy, right? But then WKB approximation and all these things we are considering become questionable. And we are assuming that if you're close enough, you can neglect the other orders. Sorry. So is that clear? Yes? So if you consider then that you have a right-hand barrier or a left-hand barrier, then you get these expressions. And what I want this to move. Every time I have the chart on, it doesn't move. Come on. Move too much. So for simplicity, you can consider right-hand barrier, but you can do pretty much the same for any of them. And you reduce this to an Airy equation. Solutions are Airy functions if you do this change. And what you want to guarantee this, if you haven't had a look, have a look at the asynchronous lecture. You can manipulate this, you want to manipulate these solutions and the asymptotic forms so that when you are in the limit of being far away from the turning point or far enough from the turning point, they converge to the WKB formula. Obviously, you have to be careful with phases. You have to be careful of how this changes across the barrier. So it's pretty much when you have those arbitrary constants and you have to look for your boundary conditions to make the whole thing continuous. But now you have to take into consideration that exactly at the turning point, your wave function is going to diverge. So you have to match with something else, which are your Airy functions and combinations thereof. I'm not going to solve it here, but what you get some connection formulae, which relates WKB wave functions on one side and the other side of the barrier. I saw something in chat, but it's not coming. It's so annoying. Either it's the chat or the, now the chat came and I left. Am I still sharing the screen? No. No? Yes?
No.
No, okay. Because I clicked in the chat and, okay. So in the chat is why not using array functions everywhere? Switch on. Well, the problem of using array functions everywhere is that at some point your approximation is no longer going to be valid, which goes back to the question that Tim was asking. Why is it approximately linear? I said, okay, it's an approximation. You have to be close enough of the turning point so that you can neglect the other terms of your series expansion. However, once you move so that you have to match the asymptotics or the WKB approximation starts to be valid, then you are in a situation that this linear expansion is going to break down. You have to do some matching. So ideally, what we would like to have is some solution that is valid everywhere, which for those who have heard of this is called a uniform asymptotic expansion, but it is something we're not going to discuss here and sometimes cannot be achieved, but ideally that's what you would like to have. But we are in a situation in which you have very good behavior far away from the turning point, very good behavior around the turning point, but we don't have things that are valid everywhere. So we have to guarantee that one matches well when you go to the other. Correct? Is that clear? It's an important point because all this matching and this connection formula, they come from there. So share. You know, I cannot look at share chat, and when I look at the chat, my PowerPoint stops. It's really annoying, but it seems that is live at the moment. Concurrent slide. Okay, so what we were discussing is that you need, let me switch this off, it's less distracting maybe. Anyway, we continue. We stop soon. So how do you go across a barrier? If you're coming from, if you have a right-hand barrier, meaning left-hand side classically allowed, right-hand side classically forbidden, what you observe is if in the classically forbidden region you have this an exponentially decaying wave function, you're going to get, to satisfy these conditions that we were discussing, this type of wave function on the classically allowed region, which is on the left-hand side. And on the other hand, if you have this oscillating wave function, the sine wave function, on the classically allowed region, you're going to get something that is exponentially increasing. So these arrows we're going to see, they indicate the direction for which it is safe to use this connection formula. For instance, if I go from here to here, I know this is going to hold, but if I go from here to here, I don't know, I may be overlooking something. And this is the same here. Left-hand barrier, if you are on left-hand barrier, just to remind you, left-hand side classically forbidden, turning point A, right-hand side classically allowed. So this is what you would obtain. You have something exponentially decaying. On the other side, you get a cos. You have something which is a sine, and you have an exponentially increasing expression. Note that the arrows, they indicate the direction for which it's safe to use this connection. And we're not going into much depth how you link these things, and you see a bit more detail on the asynchronous lecture, but still, if you really want to know, this can be an art it's not difficult, but it's fiddly. And you find some explanations in Joachim, you find in Landau, and Mersbacher is also quite good. And what happens is when you have exponentially increasing wave functions in the classically forbidden regions, and you may mask something that is exponentially decaying and you get the wrong expression in the classically allowed ones. And what I would like to do now is, it's going to take a while, but I think it's quite useful because you really need to see live how these things work. So I'm going to stop with the PowerPoint, stop share. And what I'm going to do is I'm going to do some kind of whiteboard derivation in which we are going to see an application. And this is going to be, I mean, you always, you know these square wells, right? Finite, infinite. And what we're going to do is we're going to see what happens if you have a smooth well. How can you come up with a quantization condition? So this is, I want to get rid of this. Something that is, again, not difficult, is fiddly, but is important if you want to understand how this works. So what I'll do is, okay, as server is running, allow all sorts of things. I'm just mirroring my iPad, but it should be quite quick. Okay. And here we are. And we're ready to share again. So I'm going to share my screen. Let me switch off the video, share screen. And what we are going to do now is we're going to have a look at applications. So this is a quite nice WKB application. There's another one which I'm going to release on Thursday. So application. And this is concerned and this is related to bound states in a quantum well. And the assumption that we would like to make is the following. We're going to have a particle of energy E in a quantum well Vx and this is chosen such that E is lower than the maxima of the potential. On both sides. So what I mean is following. Let me draw this potential and you're going to understand hopefully what I mean. So I have Vx as a function of x. It looks like this. And we have a particle with energy E. So that, okay, this should be constant. It's difficult to draw some straight line here. It's better. Okay, straighter. So, and we have here this turning point at x equal a and at x equal b. If we look, we can see we have three regions. We have region 1, which is classically forbidden. We have region 2, region 2, which is classically allowed, region 3, which is classically forbidden. So this means that we're going to have two turning points. We have here what we call left-hand barrier, and here we have a right-hand barrier. So let me write down, just for being specific, the turning points are A and B, the classically allowed region. Two, the classically forbidden regions. One and three. Just that we keep these things in mind. So we know, because this is something that we have discussed, we're assuming we don't have any reflections or anything else going crazy in this potential. And we know what we can say for the classically for the wave functions in the classically forbidden regions. No? So we're going to use what we know, right? So wave function, if we follow WKB approximation and we want to write the WKB wave function in 3 and in 1, we're going to have that in 1 is going to be exponentially decaying, right? It has to be, because it goes down and you have just this barrier here. So we have something of this form, psi1x, a1, square root of qx, e minus, now x integrated from some generic x to a qx dash gx dash divided by h bar. Okay. So this is wave function in 1. It's exponentially decaying. Turning points, you have to be careful. We also know the WKB wave function in the region 3, right, which is this region here, we can use the same argument. Now here, just that is clear. We have that Q is square root of, let me make Qx. Qx is square root of 2m Vx minus E. So a function in region 3 is also classically forbidden. So we can say that psi 3x is given by this expression. Going from B to X, so you have this starting point here, and you move towards X, and you're going to have Qx dash dx dash divided by h bar. But we want to know what is happening here, right? So to see the strategy, we started from what we knew for sure, that we didn't have anything that was increasing exponentially in the two classically forbidden regions. And we can use then these wave function to derive whatever you have in region 2, which is something that is a bit more involved because you can have reflection, you have transmission, and the region is classically allowed. So the wave function in 2 will be derived using connection formula. There is a question. Let me see. I don't know what happens always with this share and chat, but trying here. Yes, but look at the limits. We are taking it from X to A. So you have some kind of function which you take from wherever you are to the turning point. So you need to be a bit careful on how you define the limits. And A, which is the turning point, is bigger than whatever your X is. So you really need to access your situation. So let's have a look. Someone left. Okay. I don't know. Scrolling things. No, it doesn't. In each currency, it doesn't. We're going to have a look at this in more detail. Actually, there's a very good example in the second when we look at transmission. You need to guarantee it doesn't go to infinity. So we're going to have a look. And if you move from 1 to 2, we are going to need those connection formula. So if you look, let me see, I may have this, when you had this kind of behavior. This is going to be interesting to go to the PowerPoint again. So 1 to 2 is a right-hand barrier, right? So just to remind you, slideshow from current slide. My screen share is paused. Yeah, I know, new share. Can you see the connection formula?
Yes.
Because we had, yes, can you see? Thank you. We had in region 1 this expression, and with regard to being minus infinity or going to you don't want this to explode. If this goes to minus infinity, you have to be careful also with this upper limit here. So if you see the connection formula, you expect if you go from 1 to 2, that this is a left-hand barrier. Yeah, it's a left-hand barrier from 1 to 2, right? So you would have then, where's my pointer? Here, you would have a cos in that region. You would have this expression. So I'm going to stop the share and share the other one. And this is getting a bit confusing this. So I'm sharing the screen. Okay, the one I wanted to share. Very good. Which means that from 1 to 2, you are going to have psi 2x 2a1 square root of px cos ax px dash dx dash divided by h bar minus pi over 4. So what I have done is I applied those connection formula that you see and that I stated being a bit mystical, but the key idea, even if it looks a bit mystical, is that you have to find a way of making your function match everywhere. So if you find some airy functions around the turning point, when you go asymptotically to the WKB wave functions, they have to be matching, and this is going to lead to all sorts of phases and so on. I cannot, either I do one or the other. And I keep on saying I need a co-host. Anyway, so I have a look at the chart later on. So when I go from 3 to 2, I'm going to have a right-hand barrier, and I need to follow the arrow again. And this is going to give me this expression. Now this looks weird, right? We have two wave functions, but they have to be equal. Do you agree? They need to be equal. So because both of them have been defined in region 2, but coming back from one side and then coming back from the other side using the connection formula. So both wave functions must be equal so that we can say that 2a1 square root of px cos integral from a to x px dash dx dash divided by h bar minus pi over 4 is equal to 2a3 square root of px. I'll put this downstairs, isn't it? 2a3 square root of px cos integral from x to b px dash dx dash divided by h bar minus pi over 4. Okay, so that has to be equal. Let me see, there was something in the chat. I'm not coming to the chat, I don't know what is going on. Anyway, so, but look, we want to get these constants right, we want to get some conditions right, but how can you compare these things if here you have an integral growing from a to x and here you have an integral growing from x to b? We can perform a better comparison. If we use, or you can choose the other way around, but the important thing is that the limits in the integrals have to be the same. So you're going to have xb equals to ab minus ax. Okay, so I'm going to change this guy and I'm going to rearrange the limits, which means that I'm going to write psi 2 as 2a3 square root of px cos ab px dash gx dash divided by h bar minus ax px dash h bar dx dash here minus pi over 4. So what I have done is I want to compare these two wave functions which I derived coming from the left or from the right. I know they have to be equal, but I need to rearrange the integrals in one of them so that I can do a comparison. So I chose to rearrange this one. And I can write that integral from x to b is integral from a to b minus integral from a to x, right? If you add these two, you see these are going to kind of cancel out, and that's what you get. So I'm going, for the sake of simplicity, call this guy P, call this guy Q, and I'm going to use the fact that I can write using, if you have just some generic alpha, you can say that cos alpha is equal sine pi half plus alpha, trigonometric relation. So I can say that cos P minus Q plus pi over 4, which what I would have here, have P minus, and then you have Q plus over 4, is going to be equal to sine P minus Q minus pi over 4. So what you see is that if you use this relation and you add pi half and then you factorize this minus sign, you get your minus minus plus, and here you would have a minus. So I'm just rearranging this, and then I'm going to use also properties of when you have sine A plus B, you can write these as sine P cos Q minus pi over 4 minus cos P sine Q minus pi over 4. It is a lot which is going on. But what I'm trying to achieve is write these expressions in a way that they can be compared. And we can also get a lot of information. Because if you look, this first term matches the expression in this other connection formula which you have on this side. Because P is a constant. I wanted the wrong one. Okay. P is a constant. Q is having practically the same limits. And I need now to find what is going to happen to the rest. So I'm going to write, just in case, this matches the expression from the other connection formula. And this means that this must vanish. Otherwise, they're not going to match. So what we did is we tried to rearrange things so that we could find an expression that would match our connection formula from the other way, from the other side. This leads us to conclude that cos P sine Q minus pi over 4 has to be 0, right? Now look, if this happens, we have a few possibilities, okay? We could have either that sine Q minus pi over 4 is 0, or we could have that P is equal to 0. So let's analyze what is Q and what is P. So Q is something that varies a lot with regard to x. So if we say that the cos Q plus pi over 4 minus pi over 4 or sine is 0, this is a bit complicated and is not always going to be possible, because this would require, remember, okay, that Q is an integral in which one bound, or the upper bound, is x, so it's generic. So if I say that this should hold, this would mean that cos this would mean that this would be very specific, because this would mean that cos Q minus pi over 4 is equal to minus 1 over n, because then Q minus pi over 4 would be n pi, and this is not always possible. So this is too restrictive. Let me put it like this, too restrictive. And why can I say that? Because Q is an integral in which this upper bound is generic. If you look, you see we kept it X, where is Q here? You see the definition. We kept this X. So this is something that it doesn't make a lot of sense. But P has very well-defined constant bounds, which are the turning points, right? Ah, nice for us. So this means R cos P equals 0, which means that P is 2n plus 1 pi half. Agree? What does this mean to me? This means that P, this P capital, okay, is not the P momentum. Let me make this capital so that you know. So remember that P is integral from A to B, Px dash gx dash divided by h bar. Okay, this is our capital P. So we can say that integral from AB Px dash gx dash over h bar is n plus 1/2 pi, n equals 0, 1, sorry, 2, etc. is an integer. Do you realize what is this? This is a quantization condition. So we can actually conclude that the momentum and thus the energy in this well is quantized. So we're going to have discrete states. It's a big implication. Remember that momentum is Px equals to 2m E minus Vx. And what I'm saying here is that this must be satisfied. And n are discrete values. Now remember that remember that square well also led to discrete values for E and P, right? If you remember and you solved it. Now we know as well that if cos P, because we need to find all these expressions and all these things. So if cos P, just to wrap it up, if cos P, P capital is equal to 0, then we can say that sine P is minus 1 over n. And we had this somewhere. We had this up there. So we had some sine P as well. Remember here that we said, this agrees. So we can write psi 2, I'm putting the dependence here back, equals to 2a3 minus 1 over n divided by Px cos going from a to x, p x dash, t x dash, h bar minus pi over 4. And by comparison, we can say that a1 is equal to a3 minus 1 over n, because the wave functions, if you come from one side or from the other side, they have to be equal. So if you look, we had this expression here. If you went from 1 to 2, region 1 to region 2. So the objective of doing this is to show how you can use WKB approximation to cross from one region to the other. We were dealing with a right-hand barrier and a left-hand barrier, and to use some physical intuition, certain things that we know, to be able to deal with these situations. There are some people are asking, why did we consider cos earlier? Some people like the derivation. It will be available online soon once I have finished here, so don't worry too much. What you need to do with derivations and why I considered cos q minus pi over 4 is because first you have to see what is going on when you go from one region to the other, and you have to consider the matching between the area functions and what you have asymptotically. And then you also have to consider it in a clever way, because you know from whatever region you go, 1 to 2 or 3 to 2, the result you get in the middle has to be the same. And this is important because the physics has to be the same. So you can start from the other one if you want. You just have to make adjustments to ensure that they are the same. And if you really consider that across the barrier, this is continuous and is unique, has to give the same value, you're going to get some quantization condition. So we can, where is the last slide? This will be available online. So it's not, I can share this guy, you mean? Okay. So this is the last slide. It seems to be on AirView. So this is this thing. And you know, so what I like about it is that now, in principle, you can consider any type of barrier to find a quantization condition. You don't have to be only fixed upon a square well. Yes, you can find this calculation in actually quite a lot of books. Like from the top of my head, Mersbacher, Joachim, and Landau and Lifshitz, I think they have it. It's a standard derivation. You have this also in the notes, and I'm gonna put this also online. It's a bit scribbled, but I think it also helps. Okay, so we're done for today. Next lecture, we're going to start to talk a bit in more detail about unitary transformations and quantum dynamics, especially if you go from, we're gonna make use of these phases, global phases that are a bit arbitrary in a time-dependent setting. And then afterwards, we're gonna move to time-dependent perturbation theory, which is also very cool and absolutely powerful. So I hope you enjoyed today. Stay safe, have a nice evening, and I'm going to stop recording now. If